like to talk about the area under a curve. First of all, let's just think about area. We know how to find the area of various shapes. We know that a rectangle is just length times width. And if we had a triangle, it's 1/2 the base times the height. If we start to get an area that's more complicated, we often can divide it up into areas of things we know and then sum them together. So we could figure out the area of 4 different triangles here and then add them together. But what if we had a curve and we're interested in the area under the curve that didn't nicely divide up like these other ones? That's what we're going to talk about. So let's start with a little simpler curve first. Let's look at the curve y equals x squared, and we're interested in finding the area of this curve when the x goes between 0 and 1. So it's the shaded region here that's labeled S. Let's think about what we could do. We could divide this up into various pieces. Here the sum would be S1 plus S2 plus S3 plus S4, but it's still a weird shaped thing at the top. Well, what if instead I made that into something I could compute the area of, so rectangles? So what if we decided to divide this up into 4 intervals, and we would make a rectangle by looking at the function value at the right side of each of these intervals. And once we found the functions there, we would just go ahead and make a rectangle, and then we could figure out the areas of these rectangles and we can add them up and we get an estimate for the area under the curve. Now, if we're looking at how wide these are, this rectangle is 1/4 wide, and how high is this? The curve is the function y equals x squared, so this point right here is 1/4 squared, and this point right here is 1/2 squared, and then 3/4 squared, and then 1 squared. So we could add those up. Now we see it would be an estimate, but it would be a pretty bad estimate because we've got all this area here, 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 and here that's going to be added in there that shouldn't be, so we're going to overestimate. Now here is the sum if we added up those 4 rectangles, each of width 1/4 and height, the function value on that right hand side, so 1/4 squared, 1/2 squared, 3/4 squared, and 1 squared, and when we add those up we get 15 30-seconds. And we know that the area would be less than this because we've got all those pieces that are above the curve that we added as well. Well, what if instead we decided to look at the left-hand side? So we divide this interval up, and here we wouldn't make a rectangle because it's 0. Here on this interval from 1/4 to 1/2, we could use the function value on the left-hand side. Then from 1/2 to 3/4, we could use it on the left-hand side, and 1/4 to 1. And we could make these rectangles and we could sum them up. We're not overestimating anymore, but you can see that we would be underestimating because we aren't counting those pieces I just marked there. So this one, we're using an L for the left-hand side, and we add up those 4 rectangles. They're each 1/4 wide, and they are x squared high, where x being 0, then 1/4, then 1/2, then 3/4. We would get 7 30-seconds, and there it is as a decimal, and that would definitely underestimate. And so at least we've got an estimate for the area. It's not very accurate, but we've got an idea. Well, what if instead we said, well, let's just make some more rectangles, and we could use the left end points and we would be underestimating. We could use the right endpoints and we would be overestimating, but we could kind of narrow it down and we would be better because you can see that where I underestimate here is not as large of an area as I was underestimating when I only had 4 rectangles, and same with the areas where I overestimate. So we could be a little better off. We got to do more work though. We've got to add up 8 rectangles, but we're going to get a more accurate estimate. And if we did that, we would get these values here. So I didn't sit and work out each one, but we would work them out the very same way. This time they're going to be 1/8 wide, and then if we were using the left end points, we would have 0 squared for the first one, and then 1/8 squared, and then 2/8 or 1/4, and so forth. So you can see that we could add them up the same way, get a little more accurate. This would lead us then to the idea that we would want to make more rectangles so we could get more accuracy. So here we are looking at the left-hand endpoints and drawing the rectangles, and we would see that what we get for the approximate area. Well, what if we made more rectangles and more rectangles and more rectangles? And you could see what would happen. Now I've made this up to 40 rectangles, and I am underestimating, but the places where I'm underestimating are much smaller. If I use the right hand endpoints, I would be overestimating, but again by a much smaller value. Let's make some more rectangles, and you can see if we had 100 rectangles, I'm overestimating, but boy, not by as much. Left hand, you can see I'm underestimating. You can see that little bit of white, but not by a lot. We could continue this up to 200, and I am not underestimating by far, and I am not overestimating by far either. So that's going to be strategy here, is to say, well, we could make more rectangles to get more accuracy. More work for adding up the rectangles, but we improve the accuracy. So if we had 50 rectangles, you can see if we did the right hand endpoints, we would overestimate, but our areas are quite small. There's a lot of them, but they're pretty small. And if we did left hand endpoints, there we go. So now we are going to see that if we take the limit as the number of rectangles approaches infinity of the left hand sums, when we use the left endpoints, that would actually equal the right hand sums if we could let n go to infinity, because as we made more and more rectangles, these values got closer and closer. So let's look and write a formula for the right hand sum when we're adding up the right endpoints. And if we took this interval and we divided this interval from 0 to 1 into n pieces, so we had n rectangles, then each width would be 1 over n. So we've got 1 over n multiplied by the height of that rectangle, and the height of the rectangle is just going to be the value there squared, so 1 over n squared. Plus, now as we do the next rectangle, the width is still 1 over n, and you see all these widths would be 1 over n, but now the right hand side of the interval is going to be 2 over n, because the first interval was 1 over n, we added another 1 over n, that's going to be 2 over n. The next interval is going to be 3 over n, and we need to square them because y value is x squared. So we could say dot dot dot, and the last one would be n over n, or 1 squared. Now as we look at these, if we want to try and simplify these a little bit, we could factor a 1 over n out of every term here, and in fact we could also factor out a 1 over n squared. And when we do that, then we could combine these two things that we factored out, and we'd have 1 over n cubed plus 1 squared plus 2 squared up to n squared. And if we're interested in finding out this sum, and then we're going to take the limit as n goes to infinity, we actually have a formula for the sum of the squares of the positive integers, and here is the formula. And so we could replace this part right here with this formula, and then we could go ahead and multiply the 6 times the n cubed, and then cancel this n with this n cubed, and so here is what we would get. Now what I'm interested in is the limit as n approaches infinity, because if I can figure out this limit, then I will know what this area is. So let's see, this numerator would be 2n squared. As I multiply this, outers would be n and inners would be 2n, so plus 3n, and last would be plus 1. So let's go back to remember what we know about finding limits. I'm going to multiply numerator and denominator by 1 over n squared, and that would give me, I'm just going to move over here to fit it in, the limit as n approaches infinity of 2 plus 3 over n plus 1 over n squared, and that's going to be over 6. And as we let n go to infinity, this is going to go to 0, and this is going to go to 0, and we can see we're going to get 1/3. The area under this curve from 0 to 1 of x squared is 1/3. Let's look and just see, as we let the number of rectangles approach infinity, what our left hand endpoint sum and our right endpoint sums looked like. So here is a table. We had 10 rectangles, and this was our left sum and our right sum, so we know that the actual area is somewhere between those two. And here's 20, 30, 50, and you can look there, and as we look at 1,000, we can see that the left and the right are approaching each other. They're still not equal yet, but if we could let n go to infinity, they would be equal, but we can see that they are indeed approaching our value of 1/3.